So continue. So last time we defined this Dirac-Bragg Cat state and also derived this so-called unit operator, which is the matrix formed by this product between a Dirac Cat state and Dirac-Bragg state, where this Cat state is on the left-hand side and the Bragg state is on the right-hand side. So last time I forgot to sum over this eigenstate labeled by n. So let me just repeat this derivation to get this unit operator. So as I mentioned, the Dirac Cat state is formed by a column matrix, which is n by 1 matrix, and the matrix elements are ranging from the psi 1 to psi n, but this is the nth eigenstate in the eigenbasis. So, and the Dirac-Bragg state is a row state where these matrix elements are the start of the psi 1 n up to psi n n. Again, so we need to sum over all the eigenstates or different eigenfunctions. So when you take this matrix product, you form n by n matrix, but inside this matrix you have this n square matrix elements, but only the diagonal elements are finite and all the off-diagonal elements are 0. But if you look at this diagonal elements, you have the summation over n, and inside the summation this is psi n star 1 and psi n 1, which is the square. Remember this orthogonal normalization condition for all these eigenstates, right? So for any eigenfunctions, so this psi I star psi I is actually the same as psi I squared, but this is the nth eigenfunction, and if you sum over all these eigenfunctions or sum over n here, you get 1. So this is by normalization condition. So in the same way, if you sum over n for all these diagonal elements, you find all these summations equal to 1. Okay, so you get 1, 1, 1 along the diagonal and 0 along the off-diagonal element. So this is, by definition, the unit operator or unit matrix. Okay, so we will use that many times, and we could insert this unit operator any place, anywhere, anytime we like. Okay, so this is the power of a Dirac notation. Okay, so we have a unit operator. We can insert that any place. Okay, so let me just remind you this Dirac notation, which is the inner product between Dirac-Bragg and Cat state, where the Dirac-Bragg state is again the operation A acting on phi, which is again another Dirac-Bragg state. Okay, so and you could insert that complete set of eigenfunctions to get to this definition of this matrix element of the A dagger or acceleration value of the A dagger operator. So we could again use this notation to check the earlier, say, statement that this wave function, which is the eigenfunction of moment operator, is actually this plane wave function. And the way that we prove this is, again, we consider this projection between this any arbitrary Dirac Cat state onto a position eigenbasis, and this projection, by definition, or from what we found last time, is precisely the Schrödinger wave function. Okay, and you could play the same game right there. So you could insert the unit operator any place, anywhere I want, and this is the place I want to insert this complete set of eigenstate. And remember, this P represents this momentum, so this represents this expansion of the complete set of eigenstate of a momentum operator, which is again a unit operator. Okay, but now instead of a discrete summation, we have a continuous integration over momentum variables. So I can insert this resolution identity or identity operator right here. Okay, in the middle between x and psi, then I can simply just expand this expression and look at the different combination of this Dirac-Brand cascade. So instead of a yellow circle, I look at its red ones. Okay, so if I look at the red ones, so I get this projection between Dirac cascade, which is a momentum eigenstate, and onto the position eigenbasis as a Dirac state x, and also this projection of a psi onto momentum eigenstate p. And by definition, this projection is precisely what we defined earlier as the momentum space wave function phi of p. And so we actually go to our chapter 1 and chapter 2, and we find this Fourier transformation between this real space Schrödinger wave function and momentum space wave function, which is nothing but a Fourier transformation. And this is what we have before, and this is what we have now. Okay, so these two expressions should be identical. Okay, should be the same. As a result, this projection, or this inner product between this momentum eigenstate onto this position eigenbasis, is precisely the Schrödinger wave function of a momentum operator eigenstate. Okay, so this is psi p of x that we discussed at the very beginning of the class. Okay, so you can see that I could just use this very simple notation, this projection between Dirac-Cat and Bragg states, to represent a set of wave functions or eigenfunctions, whatever. Okay, so this greatly simplified notation in the following calculations. So let's just go on and take advantage of such a great symbol invented by Dirac, and we defined operator called projection operator. This is also a very important operator in quantum mechanics, which is based again on this unit operator. So remember this expansion theorem, which says that any arbitrary quantum state could be decomposed in terms of linear combinations of all different eigenfunctions, right? Okay, and the way that we show this theorem is that the orange circle is nothing but identity matrix. Okay, but the advantage that we benefit from this expansion theorem is that we could decompose this kind of a expansion in terms of a coefficient Cn times an eigenstate n. Okay, so now let's just define this so-called projection operator P or Pn, which is defined by this ensemble, this matrix product between this Dirac-Castet on the left and Dirac-Bragg on the right. Okay, so this is precisely the matrix element I wrote right there before we sum over n. Before we sum over n, so this is a matrix formed by this matrix element. Okay, so let's just look at what this operator tells us. So this will have this property that it could actually project any arbitrary state onto an eigenstate n with some probability amplitude. So let's just try to see the property of this Pn operator. Suppose I make a product between these two projection operator Pm and Pn, and I can simply just plug in the definition, which is this, right? So this is Pn and this is Pn. But of course, you could look at this product in a different way, right? Because you remember this kind of projection between a Dirac-Castet on the right and Dirac-Bragg on the left is just a number, because this is just an inner product between two, say, quantum states, and this is simply just a number. But what is this number telling us? Well, for a complete set of eigenbases, this inner product is nothing but delta function. Remember, a Kronecker delta function, right? Because this is nothing but dx psi m star psi n. This is nothing but delta m n. Okay? By orthogonal normalization condition for a complete set of eigen functions, so this projection, or inner product between this Dirac test on the right and Dirac-Broglie on the left, is nothing but Kronecker delta function. And so this is this delta mn, and then this is just a number, right? And then you can simply just move this number around, and the remaining part is nothing but this Pn operator, because this is the same as delta mn. You got m cascade on the left and n Broglie on the right. But you know that when m is not equal to n, this term vanishes, and this term survives only when m is the same as n. As a result, this is the same as you simply just replace m by n. Okay, but what is this? Well, this is by definition is the projection operator, Pn. So you immediately see that if I simply just square this projection operator, meaning if I make a product of Pn by Pn, and I get the same projection Pn. Again, because of this orthogonal normalization condition for a complete set of eigenstates. Okay? So, which means that if you square this projection, you'll get a single projection operator. Okay? Good. So, and there's another important properties of this Pn projection operator, which is the normalization condition. So if you sum over this projection operator over n, and this is precisely the unit matrix, right? 1. Okay, so which is precisely this unit operator right here. So, but if you do not sum over n and just look at this matrix, and this matrix is what we call this projection operator. So if you sum over all the eigenstates of the projection operator, you get back to the unit operator. Okay, so in just a moment, we will show the properties of Pn projection operator. So when we project any quantum state or Dirac cascade by a projection operator, what it does is to project this psi onto any, say, particular, say, eigenstate n with some coefficient which describes the probability amplitude that this would happen. Okay, so let's just take a short break. And so far, it's just some mathematics, linear algebra, and matrix product. So this concept of projection is really, really important in quantum mechanics. So we make that analogy to the, say, vector analysis and linear algebra, and help us to understand what is the mathematical structure of quantum mechanics, which is nothing but, say, linear operator and sort of a vector analysis in Hilbert space. So this projection that I mentioned is something you know in the vector analysis. Okay, so this is kind of a, I should say, matrix element or the inner product between Dirac cascade on the right and Dirac-Broglie on the left is nothing but this inner product between two vectors, right? So if you take the inner product between any two vectors, x and psi, this is nothing but this one, right? The magnitude of the x times magnitude of psi times cosine theta, or theta is the angle between these two vectors. You know that from your junior high school, isn't that? So, but the way that we see this analogy is based on Schrödinger wave functions. Remember, if you look at this from the Schrödinger wave function, this is nothing but psi of x, right? So this is just a Schrödinger wave function. But what does it tell us? Well, this tells us that if we just plot this magnitude of psi wave function, this tells us the distribution of this quantum state, this probability distribution of this quantum state in this x-axis. which indicates that the probability amplitudes that we can find this particle in position basis, right? But we can also project this quantum state psi onto different bases. Suppose I do not project this psi state onto x basis, but I would like to project this psi onto p basis, the momentum eigen basis, and this defines my momentum space wave function. Remember that, okay? And I can actually study again the probability distribution of this state psi when I project this state onto the momentum eigenbasis, and this tells us what is the probability distribution that I can find this particle at any particular momentum p. Okay, so and this is what I call this projection. Okay, so any quantum state psi could be either projected or mapped onto this real space eigenbasis or the momentum space or momentum operator eigenstate. And if you project this psi into the x eigenbasis, then you'll get the Schrödinger wave function. If you project this onto momentum eigenbasis, you'll get momentum space wave functions. Do you understand this? But psi is psi, the same quantum state. So it tells a very important concept, meaning a quantum state labeled by this Dirac state contains all the information that we need. The only thing that we need to do is to take a measurement, right? So when we take the measurement, we specifically project this, say, Dirac state onto any, say, eigenbasis that we like. Okay, so you can consider this psi state, a K state, a quantum state that can be Schrödinger wave functions or can be momentum space wave functions, depending on what information that we need. Okay, so this is the concept I call this projection, and this kind of projection is analogous to this inner product between two vectors in vector analysis, that if you really project this vector psi onto this x vector, and you'll get the projection of that vector in x axis. So this is what I mean by this projection. So suppose I do this quantum mechanically, and I project this, say, Dirac state psi onto the x eigenbasis, and what I get is this orange line, right? Okay, high school mathematics, inner product. And what is this in quantum mechanics? Well, quantum mechanics, this is nothing but a Schrödinger wave function. And I can also project this psi state in momentum eigenbasis. And what the projection really tells us is nothing but momentum space wave function, right? So this projection, which is this length of this blue line, right? The blue line really phi of p. Okay? So in other words, I can project this Dirac state onto any arbitrary eigenstate I like. And the amount of the projection, which is either orange or the blue, represents the wave function in that eigenbasis. Okay, so let me translate into Chinese, right? In case you do not understand. 所以我们用这个一种叫做投影的这个比喻呢，或是类比呢，只要帮助我们了解这两个概念的不同。就是狄拉克的 broadcast state， 它是一个非常抽象的量子的状态，那么它可以投影到不同的所谓本征的空间 eigenbasis， okay， 本征基底的空间。那当它投影到 x 的这个 basis 的时候，它的投影量相当于这个向量被投影到 x 轴的这个量，那它就是在量子力学里面就是我们的Schrödinger这个 wave function 好。那如果这个 psi 被投影到 momentum 的 eigenbasis 的话，那这个投影量蓝色的部分就是 phi of p。但是我们要知道的是，不管是 psi of x 或是 phi of p， 它都是从 psi of 这个 state 来的，同一个 state， 它可以被投影到不同的 eigenbasis， 就形成不同的 wave function。但这个 state 还是这个 state。就是这个 state 它拥有所有的这些你要知道的资讯都包含在里面，但是你必须要去投影它。You need to project. All right? Okay. So later when we discuss angular momentum or spin angular momentum operator, and you will know that difference between any arbitrary state labeled by Dirac, Kerr-Bragg state, and this Schrödinger wave function or momentum space wave function. So there's some subtle difference between these two concepts. Okay, so Schrödinger wave function and momentum space wave function are simply realization of an abstract Dirac state. All right? Okay, so you can label this psi, if you like, by, say, momentum and position. Okay, which is maybe. So it has everything. But before we project, we don't know anything. If we want to know anything, we need to project. Tell me what you like to project this state onto. Well, I like to project it on the x-axis. Well, this is your Schrödinger wave function. What about the p momentum basis? Well, this is your phi of p. Right? Okay, so this is the analogy that I use to describe the difference between this Dirac-Kerr-Bragg state and the realization of that Dirac-Kerr-Bragg state. It's like I'm wearing a t-shirt today, but I'm wearing a suit tomorrow, but I'm the same person, right? So when I wear a t-shirt, I look like someone else, but if I wear a suit, I look like another person, but these two persons belong to the same person. Okay, and that same person is this psi. Okay, and this is the great advantage of using Dirac notation. I suppose everyone gets the idea and analogy, so let's just go on and discuss this projection. So let's just project this using this projection operator Pn, and we project this Dirac state psi, and this is what this is in psi, right? Okay, so as I mentioned many times, that if you look at this, you should find this matrix element which gives you a number, and this is the number because this is Dirac state on the right and Dirac-Bragg state on the left, so you get a bracket. So whenever you get a bracket, this is a number. But if this is not bracket, and for example this Dirac state on the left and Dirac-Bragg state on the right, and this is this kind of shape, and if you look at this stuff, and this is not a number, but a matrix. Right, so it is easy to distinguish between a number, which is the inner product between two vectors, or two, say, Dirac-Bragg states, or it is the operator expanded by a Dirac-Bragg state. Okay, so when you have that expression on the right-hand side, you must look for a number, and this is a number marked by yellow. So what is this number telling us? Well, this is nothing but some coefficient, right? So this is some coefficient, and this coefficient is defined by Cn, And again, Cn is the coefficient corresponding to the probability amplitudes that you can measure that there's any arbitrary state to be in any particular eigenstate n. Okay, so this has the property that when acting on arbitrary state psi by this projection operator Pn, and this Pn operator projects this arbitrary cat state onto eigenstate, and with the probability coefficient, which is Cn, which is again the inner product between the Dirac cat state on the right and Dirac broad state and on the left. Right? So if you notice that this is nothing but this coefficient in your expansion theorem, because in your expansion theorem it is given by this, right? Okay, but what is this? Well, this is nothing but this kind of projection operation, right? So you could project your arbitrary Dirac cat state onto the particular eigenstate with some probability amplitude, and this is precisely the definition of this projection operator. So you can project this psi by this Pn operator, projection operator, and when you project this psi by Pn, it gives you this coefficient Cn times this eigenstate n, right? And the Cn is nothing but the probability amplitude that you will find that the state psi to be in that particular eigenstate. So it's like take a measurement, right? So if you like this Pn, really take this measurement onto this any arbitrary quantum state psi, and after you take the measurement, you have a probability amplitude that you'll find that this arbitrary state psi to be in a particular eigenstate. And the probability amplitude is given by this coefficient Cn. Okay, so remember, if you really want to actually link this to this probability, and the Cn squared is your probability. Which means that if you take this kind of projection many times, and each time you may project the state psi onto different eigenstates with the different results, but if you perform such a projection 100 and 1,000 times, then you take the statistical average. You just look at the numbers, how many times that this projection will go to some specific eigenstate, and you'll find that the probability that this measurement gives you the state n is precisely Cn squared. Okay, so you could use this projection operator to understand this expression value of the system's energy, as we already discussed many times, but we will do it now, but using the Dirac notation, is that you could take this expression value of the Hamiltonian and sandwich by this arbitrary quantum state, and you could just take this measurement to find out the energy of that state psi, right? So if you have arbitrary quantum state psi and in the system defined by the Hamiltonian, and I could just take this expression value of a Hamiltonian sandwiched by this any quantum state, which is associated with this Schrödinger wave function. Remember, this is nothing but the Schrödinger wave function, right? If we simply just consider this psi as the Schrödinger wave functions, and this is, by definition, is the expression value of the Hamiltonian. But you could also understand this in a Dirac notation, meaning this is the expression value of a Dirac cascade, or it is the energy of a Dirac cascade. So let's just do it using this projection operator. So you could actually, again, decompose this psi in terms of this kind of linear combinations of all eigenstates with the proper coefficient. And when you do it, you'll find that this is nothing but the probability that you take a measurement and the result of a measurement gives you an eigenenergy En, right? This is nothing but the probability finding states to be at n eigenstate and eigenvalue En. But I can rewrite this well-known results in terms of a projection operator. So what I do is just to re-express this in terms of a projection operator. So, well, this is the probability of finding this state psi to be at eigenstate n and eigenenergy En, but I can just re-express this in terms of this two different conjugate, matrix element or inner product, and I can move around this eigenenergy En any place I want, and so I could just have that product of these two matrix elements. But we know that this is the definition of projection operator Pn, right? Okay, so then you could simply just use this identity or this equation that we derive right? But then, well, this is equal to this projection operator, or this is the probability at En, right? So, yeah, so you can simply just use this result that we have right here, and to actually understand this kind of a expression value of a Hamiltonian, which is the energy of a quantum state psi, which is nothing but this summation over all different eigenenergy multiplied by the probability of finding that state to be at that particular eigenstate and eigenvalue En, right? So, but what is this inner product between psi and n, which is nothing but this amplitude, probability amplitude, that if you use the projection operator acting on this arbitrary quantum state psi, and you'll get the coefficient Cn, which is this one, and if you square this Cn, you get the probability n, which is exactly what we have right here, right? So this is the square of that coefficient. So you could consider this as the probability of finding the state psi at particular eigenstate and multiply by this eigenenergy, and you sum over all this eigenstate n, and you get expression value of the energy of a particular quantum state psi. Okay, and this matrix element is nothing but this Pn right here, where Pn is simply just Cn squared. Okay, so in other words, we could understand this kind of expansion theorem in terms of the projection operator. So, and you could project any arbitrary quantum state onto a particular eigenstate with some probability amplitude. And so you could really consider this projection the same thing as you take the measurement. Okay, so, and because of this probability interpretation of this coefficient, you could really interchange these two words, that you project this arbitrary state it means that you take the measurement of that state and you see the outcome of the measurement. And the outcome could be only at any particular eigenstate. Of course, this is what quantum mechanics is telling us, that any quantum system, the particle can only occupy at this one of its eigenstate, right? It cannot be at arbitrary state. It can only occupy it at particular eigenstate. So if you take a measurement of something, of some state, and it can be found in any of these eigenstates with some probability distribution. And it is very convenient to actually use this projection operator to take the measurement. Okay, so let's take a short break. When we come back, we will derive this Heisenberg uncertainty relation that we discussed many, many times, but this time we formally prove this Heisenberg uncertainty relation using the Dirac notation. So this is a really powerful method that allows us to really derive fundamental principle that the Heisenberg uncertainty relation could be derived at a general level. Okay, so as I mentioned, the product between two standard deviation or error bars of two measurable quantities depends on this commutator of these two operators. And if you have a finite commutator and non-zero commutation relations, and it tells us that you have this uncertainty relation to be satisfied, but you have these two commuting operators, and you can actually determine all the information in 100% accuracy at the same time. So this Heisenberg principle can be proved and derived based on Dirac notation. Okay, so, and let's take a short break. When we come back, we will derive this officially. Okay, so let's just prove or derive this Heisenberg's uncertainty relation. So as I mentioned, it is very convenient and useful to use Dirac notation. And so let's just define this inner product between a Dirac cat and Broad state, f and g, in terms of a Schrödinger wave function. You can consider this f as some quantum state represented by the Schrödinger wave function f star of x, and g as a Dirac cat state represented by this g of x as a Schrödinger wave function. And you take this, say, overlap between these two wave functions, and you define this as what I call this projection of a state g onto the state f, right? Okay, so this is the definition. And we will try to use that relation or use the definition to actually prove this uncertainty relation, right? So, and we could use this analogy between this Dirac-Broad cat state and inner product between these two quantum states and the vector analysis. As I mentioned, this kind of a projection between Dirac cat and Broad state could be understood in terms of analogously the inner product between the two vectors A and B, right? So, but we know that in the vector analysis that the dot product between A and B vectors is always smaller than or equal to the product of this square of the magnitude of the A and B vectors. Okay, so we could make analogy in this quantum mechanics by using this inequality, and in quantum mechanics this corresponding inequality is called Schwarz inequality, meaning the magnitude of this integral is smaller than or equal to the square root of this square of this integral of the square of these two functions. And you multiply this to integral like this. So you could consider this f of x as some vector a, and g is some vector b. So this kind of projection between g and f could be understood in terms of a dot b. So you take the magnitude of this a dot b. This is always more than or equal to this product of this two square of this magnitude of these vectors. And if you take a square root, and this is the corresponding inequality, which we call the Strauss inequality. And later we'll define what f and g corresponds to. So let us use Dirac notation. So when I project f onto f, this means that I take the integral, but inside the integral, this is a magnitude square of this f of x wave function, right? So now let's just define a standard deviation. When we take the measurement for a particular observable, which is defined by operator A. Okay, so this is my arrow bar, the square of the arrow bar, right? So imagine this is delta x squared, and this will be delta p squared, something like that. Okay. So by definition, the square of your deviation, when you take the measurement for this A operator, and this is defined by this kind of projection. If I define my f as this kind of operation, so f is some quantum state, which is the difference between, say, operator A acting on psi minus the expectation value of the A times this psi. So which is that in some sense this is kind of a deviation from your mean value or expected value. Okay? And if you just project this f on f, it really gives you the square of your standard deviation. Okay, so this is something like square of your deviation. And you can consider this f as some sort of a deviation. And likewise, I could define my square of the deviation for operator B, where the state G is defined again in the same way. So the Strauss inequality could be re-expressed in terms of sigma A squared times sigma B squared, which is f projects down to f times g projects onto g, which is larger than or equal to the square of your projection between g and f. Okay, so this is another way to rewrite the Strauss inequality in terms of a standard deviation. Okay, so we will see later that sigma A times sigma B is actually some sort of a delta x times delta p is much larger than, say, h bar over 2. So we will take advantage of the Strauss inequality and see that the product between sigma A and sigma B is greater than or equal to some number, and this number is related to the commutator between A and B. So let's just continue to derive such inequality. Suppose this projection, G on F or F on G, which I call this Z, which is a complex number. Because it can be a complex number, but if I square this, take a magnitude square, of course this will become a real number. But before I take the magnitude, this projection F on G or G on F could be some complex value. For any complex number z, so magnitude of z squared is given by the square of the real part plus the square of the imaginary part, right? Of course, it is greater than or equal to the imaginary part square, which is, right? Okay, so of course, we can go on to actually consider this right-hand side of the Strauss inequality as some sort of a z square, z magnitude square. So the Strauss inequality could be written continuously as sigma a squared times sigma b squared is greater than or equal to magnitude of z squared, right? And but magnitude of z squared is larger than or equal to the square of the imaginary part, which is this one, which is this one. If I plug in this definition of z, okay? So this is just the square of the imaginary part of z, and you plug in what is the definition of a z, which is the projection between g and f. And so z minus z star is nothing but this g onto f subtracted from f on g, right? So let's just try to evaluate this inner product between f and g. And so I plug in this definition of f and g in terms of a standard deviation when you take a measurement for a particular operator a or b. So this is given by, okay, so now I can simplify this inner product, and I could rewrite this. I skipped some details, but let me just rewrite this in terms of these two terms. So you could rearrange all these four different terms, and then you could show that this is given by this, the expectation value of the AB product minus the expectation of the A times expectation value of B. So this is the inner product between this G, a cat state, and F as a broad state. But this is just one term, right? So you should subtract this term by the complex conjugate of that term, right? So this F G minus G F is given by AB expectation value minus BA, which is precisely the commutator between A and B, and you take the expectation value of that commutator. So finally, we derive this Heisenberg uncertainty relation, which is if you just plug in this commutator, expression of the commutator as z minus z star, and you divide this by 2i, and you square this number, and you put it on the right-hand side of the inequality, and the left-hand side is just square product of this deviation. So you get the Heisenberg uncertainty relation, which means that sigma a squared times sigma b squared is greater than or equal to 1 over 2i expression value of the commutator between A and B, and you square this on the right-hand side. So this is the formal derivation of this Heisenberg uncertainty relation, which holds for arbitrary two operators. So you can plug in whatever operator you like for A and B. So let's just check Heisenberg uncertainty relation for x and p. So suppose I consider A as x operator and B is the momentum operator B. So I can get sigma x squared times sigma p squared, which is delta x squared times delta p squared is greater than or equal to 1 over 2I times what? Commutator between x and p with expectation value, and you square this thing. Okay, but what is the commutator between x and p? Well, this is what? H bar, right? IH bar. So you get IH bar on the right hand side, where I cancel with that I in the denominator, and you get H bar over 2, and you square this. So now you take the square root of everything on both sides of the inequality, you get precisely the Heisenberg uncertainty relation, where delta x times delta p is greater than or equal to H bar over 2. All right, so this sounds magic, but there's no magic at all. So it only tells us that if you want to take a measurement for two different observables in quantum mechanics, and there's an inequality that we need to obey. And this inequality tells us that the product of these two standard deviation on A and B operation should be greater than or equal to the square root of this, the commutator, divided by 2I squared, which is, this is the lower bound of this product arrow bar. And you can plug in any operator you like. Suppose this is the x and p, but you could also consider this a parity operator and momentum operator and so on. Or you could plug in A and B as what? Angular momentum operator and the spin angular momentum operator and so on, or a Hamiltonian operator and a spin angular momentum operator and so on. So you could derive many different uncertainty relations between any two measurements, and depending on whether these two operators commute or not, if they do commute and you do not have such an uncertainty relation, meaning you could determine their measurements in 100% accuracy at the same time. Okay? But if they do not commute and you do have such a Heisenberg uncertainty relation. Okay, so up to now, I think it is a general property in quantum mechanics that when we have this non-vanishing commutator between any two operators, and automatically we have such a Heisenberg uncertainty relation. So then the question is, why do we have such a non-commuting properties of any two operators? Well, so that's the thing. So this is the fundamental properties of quantum mechanics, namely when we take the measurements of two different variables and the order really matters. So which operation that we do first depends, the final result depends on which order that we take when we take these two measurements. For classical mechanics, we do not have such a restriction, but in quantum mechanics we do. And the reason that we do make a difference is because those operators, if you wish, in a mathematical form, is actually some kind of a, say, matrix operation or some kind of a differentiation, right? So, for example, this momentum operator P in quantum mechanics represents this differentiation of your Schrödinger wave function with respect to x, right? So this order matters because this differentiation, when you put it before or after different operators, the final result will be, of course, different. And it is also because we treat all these quantum mechanical operators as matrices, right? So if you understand this matrix product, of course, these two matrix product between A and B matrices is not necessarily the same as B times A. Right? Okay. So it is because of these two unique properties in quantum mechanics that we do have such a Heisenberg uncertainty relation. So in classical mechanics, we do not have such a very strange properties like this, but in quantum mechanics, we do. And the reason we do is because we treat quantum mechanical operator as a matrix, and they follow the matrix product. And the matrix product rules tell us that these two are not necessarily the same. Okay? Good. So I guess I kept my promise. I promised you that I would derive the Heisenberg uncertainty relation, and I did today. Okay? So I guess this is an important theorem in quantum mechanics that you could derive these relations using Dirac notation. So this is a very elegant way of deriving such a general principle in quantum mechanics. Okay, so let's take a short break. When we come back, we will start a new section, which is the harmonic oscillator problem by using Dirac approach. So in the following, I will use this operator method and Dirac notation to derive these eigenstates and eigenfunctions of a harmonic oscillator, which we did this by brute force, which is really not the right way to do. Okay, so, and this operator method is the method that everyone will need to understand, because this is the basis for understanding this, say, angular momentum, the spin operator, or hydrogen atom, or whatever this quantum mechanical Hamiltonian that you want to study, because we cannot solve the Schrödinger equation for many realistic Hamiltonian, but we could sort of use this operator method to simplify this calculation. Okay, so you'll see that this is really powerful and elegant and smart. And all we need is to define the operator and the Hermitian conjugate and the commutator between those operators. So let's just study the harmonic oscillator problem again. So the Hamiltonian is very simple. Okay, so, and what do we do? Well, again, as I mentioned, we need to define an operator A and A dagger, which could simplify this Hamiltonian, and we could find this commutation relation between this operator. And we will notice this kind of combination between X and P operator. In classical mechanics, this Hamiltonian is simply just re-expressed in terms of this product of two conjugate operator. Suppose you simply just make a linear combinations between X and P with the plus I and minus I in between, and you just expand this product between these two linear combinations of X and P, and you'll get back to this Hamiltonian. Classically, I mean, there's no commutation relation between X and P, but quantum mechanically, you have additional term because X and P do not commute, right? So quantum mechanically, you'll find that this kind of product give rise to additional terms. So I define this bracket right here by h bar square root times this A dagger operator. Suppose this is A dagger, and this will be my A. Okay? And suppose that I simply just multiply this A dagger and A operator, and what I get is this following. So this is p squared over 2m plus 1/2 m omega square x squared minus I omega over 2 px minus xp, which is the Hamiltonian minus 1/2 h bar omega. So if I make this product between, say, A and A dagger, quantum mechanically, what I get is the Hamiltonian subtracted by this 1/2 h bar omega, and this term marked by red is the extra term coming from this finite commutation relation between x and p. So you'll get some extra term, which is px minus xp times a prefactor. But you know that px minus xp is nothing but minus I h bar, so you plug that in and you get minus 1/2 h bar omega. As a result, you could rewrite this Hamiltonian in terms of the product between A and A dagger. Right? Okay, so this is one way to simplify this calculation by the operator method. So you could find out this commutation relations between A and A dagger, also between A and H, also between A dagger and H, and you could see what this A dagger effect and what is the effect of A is, and you could really derive this ground state by applying this A and A dagger many times. Okay, and then you could construct this eigenstate and eigenfunction based on these properties of A and A dagger. So this is the power of an operator method. It's really simple. So let me just define this A one more time. So by the way, this x and p operators are Hermitian operators. So when you take the dagger on x and p, you get back to the same operator x and p. And the only difference is this is plus I, and this is minus I here. Good. So now let's just study the commutation relation between A and A dagger, which is a straightforward algebra, because you know this commutation relation between x and p, and x and x commute and p commute, so you could very easily compute this commutation relation. So this is given by, so let me just separate this into two terms. Okay, so you could simply just look at this non-vanishing contributions of this commutator, which is a commutator between x and p, or p and x. You forget about this commutator between x and p because they are 0. So there are only two terms remain here, which is this and that, and you simply just use this commutator between x and p, and you plug here, and you multiply this prefactor, and you find that this is 1. That's simple. Okay, so now you learn a lesson that this A and A dagger, they do not commute, and the commutator between A and A dagger is 1. So we will take advantage of such simple, elegant commutation relations between A and A dagger, and we will study two different commutators. One is the commutator between H and A, another is between H and A dagger. So let's look at this commutator between H and A, which is, by definition, this is what? Right? So you plug in the simple form of your Hamiltonian, which is h bar omega times A dagger A plus 1/2, and back to this commutator, H here. So, and you forget about this 1/2 here because this is just a constant, and constant number commutes with any operator. So the only thing that you need to compute is this commutator. And you will see that this is given by what? Minus h bar omega times A. Right? Because this is what? This is A dagger times AA commutator plus A dagger A commutator times A. And we know that AA commutes, and A dagger A commutator is actually minus 1, because this A and A dagger commutator, where A appears on the left hand side and A dagger on the right hand side, and this commutator equals 1. So if you change the order between A and A dagger, remember you need to put the extra minus sign here. So this is minus 1. Good. So now, in a very similar manner, we could compute this commutator between H and A dagger, which is this one, right? H bar omega A dagger. So it is really, really simple, and we will take advantage of such simple relations and commutation relations, and we will construct the eigenstate of the Hamiltonian based on this, say, eigenstate of A and A dagger operator. So suppose this Dirac state E represents the eigenstate of the Hamiltonian or harmonic oscillator, and we could check this kind of operation. When we try to operate this commutator between H and A onto this eigenstate E, and let's look at the results of this operation. So this is given by H A minus A H, which is what? H A E minus E A of E. But what is this on the left hand side of this operation? Well, this is commutator between H and A, which is what? Minus H bar omega times A, right? So this is, which is given by what? H A E minus E A acting on E. So let me just rewrite this term in terms of a more useful expression, which is this eigenvalue equation. So if you rearrange this rad equation right here, and you will find this is the equivalent expression for the rad equation, which says that with the Hamiltonian operator acting on this orange state, and the orange state is made of this operator A acting on this any eigenstate E of a harmonic oscillator. So suppose this orange state is another quantum state, which I don't know what that is, but I simply just use Hamiltonian operator to act on that orange state, and what I get is the same states on the right hand side multiplied by the eigenvalue. And the eigenvalue of this kind of equation is the eigenvalue E minus H bar omega, which means that this, suppose I have this eigenstate of harmonic oscillator like this, and this is a particular eigenstate E. I don't know what that is, but suppose this is one of the eigenstates of the harmonic oscillator, which I know they should exist, right? Okay, so if I suppose I simply just use the operator A acting on this E, suppose I operate this A onto E, the state E, what I get is another eigenstate of a Hamiltonian, but with eigenvalue less than 1 H bar omega. Okay, so suppose this is eigenvalue E, And if I use this operator A acting down this E, I get is the lower eigenstate by one floor, which is this one. So this one has this eigenvalue E minus h bar omega, but this one is also an eigenstate of the Hamiltonian, right? Because this orange state satisfies the eigenvalue equation for the Hamiltonian, which means that this orange state is another eigenstate of Hamiltonian with 1 h bar omega less in their eigenvalue. Okay? So from our previous knowledge, we know that suppose this eigenvalue E represent that state, a top state, and E minus h bar omega state is just one floor down relative to this state E. Okay, so this is, say, lower floor eigenstate by 1 h bar omega, and we know very well that all these eigenstates of the harmonic oscillator are equally spaced, and the distance between these two neighboring eigenstates in eigenvalues is really just h bar omega. So remember that in the previous chapter, we know that there are equally spaced eigenstates of harmonic oscillator, and the neighboring states shows the difference h bar omega, or plus or minus h bar omega, in their eigenvalues. Okay, so this state, which is made by operator A acting on this some eigenstate E, is again another eigenstate of harmonic oscillator, but one floor lower, which is this guy. Okay, so this is really a good news, because we can take advantage of such operation. And suppose I know the eigenstate of any arbitrary level, and I can actually go to the lower level by applying operator A. And I can show further that if I start from this E minus h bar omega state, I can also go another lower level to E minus 2 h bar omega. And if I just keep applying this operator A onto this eigenstates of harmonic oscillator, I get to another eigenstate with a lower level by 1. And you could actually keep doing this again, then playing this trick, and you go from any floor all the way down to the ground floor. Okay? And this is called lowering operator. So by definition, this lowering operator A shows this property that if I apply this A operator by acting this operator onto any arbitrary eigenstate, and I will go to another eigenstate just one floor down. You can go downstairs one by one by applying this operator A. Okay? You could go from the top floor all the way to the ground floor, the ground state. And this is the trick of this operator A dagger. So, yeah.
我想问那个 NA 这个这两条公式是怎么来的？
这怎么来的？是不是？我的古典物理告诉我，我只要把这两个乘起来，我就可以回到这个 Hamiltonian 了。所以我可以定义 x 跟 p 的任何的线性组合，然后我可以定义这个东西，然后我把它乘起来之后，我可以用它来重新表示我的 Hamiltonian。
所以是
从这里来的啊。古典物理 x 跟 p 不会 是 commute 嘛，对不对 ？h bar 等于0嘛，对不对？所以你要不要我乘给你看？
有看。
你看出来了吗？
有。
cross term cancel， 你看出来了吗？
有。
好。
那个为什么就是 h 和 a 的 commute， 然后要乘上 1？
为什么要这样？是不是？我喜欢，我愿意，我希望，我试试看。
对，经验法则吧，就是
没有经验法则，就是你知道它的 commutation relation 的时候，你就要 try 各种的可能的 operation。All right? Okay. So this is not try and error. This is the educated guess. Because you know this commutation relation between H and A, and this is, again, another operator, right? And you want to do that operation because you know this commutator, and you know this is given by a single operator A. So why not? I simply just use this commutator operator acting on any eigenstate E, and I just want to check what that gives us. And indeed, this kind of equation gives us very important information, saying that if I look at this orange state, and this is another eigenstate of Hamiltonian with just eigenvalue subject by h bar omega. And this is the new insight that I use this operation. All right? So if you want to ask me what the hell that I know this in the first place, well, my answer is just try everything you can imagine by using all these commutation relations you have. Understand that? Of course, I would not right away think about this calculation, but one way or another, I will try everything, all the calculation I can imagine from these two commutation relations. And this is certainly one of these possibilities that I can do, right? If you try this, then you'll find this very useful information, which is this elevator thing. So this A and A dagger are like elevators, which take you from, say, the top floor all the way to the ground floor. And how do I know this? Well, this is the way that I know this. Okay, because I operate this commutator operator on any eigenstate, and I can simplify this eigenvalue equation. I discover that A acting on E is another eigenstate with 1 h bar omega less in eigenvalues. And this is the new discovery that I find. If I don't do this, I have no way to know that. But how do I know that I need to do that? Well, you tried everything, all the possible calculations that you can do, and one way or another, you will discover this. Okay, there's no mystery. There's no mystery at all. You just tried all possible ways to actually compute this eigenvalue equation, and you will always find this information, right? There's no escape. Okay, so but you may wonder, why am I doing this linear combination? Well, this is a mathematical trick, but this is a smart, educated guess or try that if we make linear combinations of x and p like this, like an A dagger, and I could simplify the Hamiltonian in terms of A dagger times A. Remember, A and A dagger are Hermitian operators, right? So, and Hamiltonian is also Hermitian operator. So this combination, A dagger times A, is a very simple way to re-express the Hamiltonian harmonic oscillator, and then you just try all these commutation relations between A and H and A dagger and H and A dagger, and then this is what you discover. Okay, so this is what we call the operator method. So you don't just solve the Schrödinger wave function and find the eigenfunctions by brute force, but you just look at this operator structure of the Hamiltonian. And this is a smart way, and this is the best way, and this is the correct way. You just look at this, all different combinations of this operator, and you cleverly find out that this is an elegant way to represent this Hamiltonian, and you look for the commutation relations of these new operators, and you will find this very simple, elegant interpretation of your eigenstate. So in other words, you don't need to actually to derive the Hermite polynomial and nothing. You just take the elevator and you can go anywhere you like, from the ground floor all the way to the top floor or vice versa, and that's it. So next time we will solve this ground state wave functions of the harmonic oscillator by this operator method. Okay, so this is the lesson that we need to learn, that all the quantum mechanical problems could be elegantly represented by some proper operator. And you just study the commutation relations of that proper operators, and you are done. Okay, don't even try to solve the Schrödinger equations by brute force. It is not possible, and this is the only way. All right? Okay. Does everyone get that? Good. So that's enough for today, and see you next Wednesday and Thursday.